Hey there and welcome. Today we're going to do something a little different. We're not just going to learn some math, we're actually building a toolkit. A really powerful set of tools that lets us measure, understand, and even predict how things change all around us. So let's open up that box and see what we've got inside.
So let's start with a puzzle. How in the world do you measure the speed of a rocket at the exact instant it lifts off? I mean, think about it. At that single moment, no time has passed and it hasn't covered any distance, so its speed should be 0 divided by 0, right? I mean, how does that even work? It's kind of a paradox. And this is precisely the kind of question that calculus was invented to answer.
And believe me, this isn't just about rockets. This one core idea, measuring instantaneous change, is the absolute key to understanding almost everything that's in motion. We're talking about the g-forces you feel on a roller coaster, the rate an infectious disease is spreading, or even what keeps planets locked in their orbits. It's the language of a dynamic world.
So, to really get a handle on roller coasters, planetary orbits, and all these other amazing things, we need a special kind of math. We need the mathematics of change.
Okay, let's dive in. The very first, and I mean the most important tool we're going to put in our kit, is called the derivative. Seriously, this thing is the master key that unlocks everything else.
So what is this thing? Well, you might be surprised, but this huge, powerful idea, it all boils down to something super simple. A derivative just tells us the slope, the steepness of a line at one specific single point, not over a distance, but in an instant. A really great way to picture this is to think about the speedometer in your car. It doesn't tell you your average speed over the last hour, it tells you your speed right now at this very second. That's exactly what a derivative does for an equation. It gives you that instantaneous rate of change.
Okay, so we know what our master tool does. Now it's time to start filling up our toolkit with the first few essential pieces. These are the rules that are going to let us handle most of the common stuff we run into.
All right, we're starting with the two heavy hitters, the most fundamental rules of the bunch. First up, the constant rule. If you have a function like y equals 5, its graph is just a perfectly flat horizontal line. And as the intuition says, a flat line isn't going up or down, so its slope is, well, 0. Simple as that. Then you've got the power rule. Oh man, this one is an absolute workhorse. It's our go-to for basically any function with a power, and it's the foundation for modeling everything from the path of a basketball to the acceleration of a sprinter.
And get this, the recipe for using it is so simple. It's just 2 steps. First, you take the power and bring it down to the front to multiply. Second, you just reduce that original power by 1. That's it. It's a super simple recipe that works on a huge range of functions.
Okay, but what happens when you've got a more complicated equation, with a bunch of parts added or subtracted? Well, that's where the sum and difference rules come in. They basically let you take a big, messy problem, break it into smaller, bite-sized pieces, deal with each one on its own, and then just stick them back together. It's all about making big problems manageable.
All right, our toolkit's looking pretty good. We've got the basics covered. Now let's upgrade. It's time for the pro-level attachments. These are the tools that are going to let us tackle the really interesting, complex functions.
So, what do you do when two functions are being multiplied together? Here's a little secret. You can't just multiply their derivatives. Nope, doesn't work that way. You need a special tool, and that's the product rule. Now, it might look a little complicated, but trust me, it's just a recipe. You take the derivative of the first part, multiply it by the second, and then add the first part multiplied by the derivative of the second.
And what about division? Yep, there's a rule for that too, the quotient rule. The formula itself can be a real pain to remember, so some genius mathematician came up with this awesome little rhyme to help out. Low d high minus high d low over the line and square the low. Say it out loud a few times, and I promise it'll get stuck in your head. It's a lifesaver.
Okay, take a breath. It's time for the big one, the most powerful, most versatile tool in our entire kit, the chain rule. This is our secret weapon for dealing with functions that are nested inside of other functions. Like those Russian nesting dolls, the chain rule is what lets us open them up, one layer at a time.
Now this is where things can get a little confusing, so let's clear it up right now. You're going to see the chain rule written in 2 different ways, and they look totally different, but they mean the exact same thing. The notation on the left basically says, take the derivative of the outside part and multiply it by the derivative of the inside part. The one on the right shows how we can literally chain the rates together. They're just 2 different ways of looking at the same process. So if you have something like the sine of x squared, the sine is the outside doll, and the x squared is the inside one. The chain rule just gives us the system to unpack it all correctly. It's how we handle complexity.
Okay, our toolkit is officially built. We've got rules for pretty much everything. Constants, powers, adding, multiplying, dividing, and even those tricky nested functions. So now, for the fun part. Let's actually put these tools to work and see what they can do.
So here's a classic puzzle you see in pretty much every calculus class. You've got a ladder leaning against a wall, and the bottom starts to slide out. The question is, if you know how fast the bottom is moving away from the wall, can you figure out exactly how fast the top is sliding down? With our new toolkit, the answer is absolutely yes. We can find that speed at any exact moment. This is a perfect example of what's called a related rates problem. Or how about this one? Imagine someone is walking away from you in a straight line. With our tools, we can figure out more than just how fast they're moving. We can actually calculate the rate that the angle of your line of sight is changing as you watch them go. It's this incredible bridge between linear speed and angular speed.
And finally, one of the most practical uses for derivatives, optimization. This is all about finding the best way to do something. So let's say you have a certain amount of fence and you want to build a rectangular pen that has the biggest possible area. How do you figure out the perfect dimensions? Well, you use derivatives. You find where the slope of the area function hits 0, and boom, that's your maximum area. It's incredibly useful.
So think about where we started. We started with this seemingly impossible question about a rocket speed at a single instant. And from that one idea, we've built this entire toolkit that can model motion, track how things change, and even find the absolute best solution to a problem. The world around us is just full of change. So I guess the only question left is, now that you have the tools, what are you going to measure first?